So this is the second part of the fission and fusion video, and today we're focusing on fusion. Remember, our aim with both of the videos is to be able to describe both the fission and the fusion processes. In terms of fission, we want to understand what a chain reaction is and what the control rods are for. And with both of them, we need to understand that large amounts of energy are released which we can use for other processes. Now, we said previously when we were doing a little overview of fission and fusion that both release energy from the nucleus of an atom, and that energy can be useful and we can use it to do other things like generate electricity. Currently, fission takes place in power stations, but fusion takes place in stars. Fission is a large unstable nucleus turning into two smaller nuclei when a neutron is absorbed into the nucleus, and with fusion we've got the opposite. We've got two small nuclei fusing together to become one large nuclei. So if we remind ourselves of fission to make sure we've got both of them to hand in our memory so we can see the differences, we're going to take a neutron that's going to be absorbed by this uranium or plutonium nucleus. It's going to split into two smaller daughter nuclides. It's going to emit gamma radiation, and it's going to emit 2 or 3 neutrons and release energy. And that energy in power stations we then use to generate electricity. But fusion, as we've said, is different. Fusion is the joining of two light nuclei to form a heavier nucleus. So if we have a look at this diagram here, we've got an equation for fusion, and this is hydrogen to helium fusion. So we take two hydrogen isotopes and they fuse together and they form helium, release a neutron and release energy. Fusion only takes place at extremely high pressures and temperatures, because you can see these hydrogen isotopes are both positively charged, so there's going to be electrostatic repulsion between them. So you need to have a really, really dense, high temperature, high pressure gas so that those two hydrogen gas isotopes can collide together with enough force to overcome that electrostatic repulsion. Currently, the conditions where that takes place is in stars. So our sun is a star. Hydrogen to helium fusion is taking place in the core of the star at the moment. And we know that stars are very hot, very large balls of gas, where we have these conditions that we need for fusion to take place. Now, if we sort of have a brief introduction as to why energy is released, and this is something that you look a lot more at sixth form physics. If you measure the mass of this hydrogen isotope and that hydrogen isotope, and you measured the mass of this helium atom and this neutron, you'd find that the mass going in does not equal the mass coming out. But what has happened is that some of the mass that has essentially disappeared has been converted into energy, and that's this energy here. And this is where you might have heard of Einstein's equation E equals mc squared. And this is saying that energy is equal to mass times the speed of light squared, and it means that you can convert mass into energy and energy into mass. And what's happened here is that we've converted some of this mass into energy, and the more mass you have, the more energy it would be converted into. So that's where the energy is coming from. It's because there's this change in mass. Now, there's actually several stages to this whole hydrogen to helium fusion process. So there's also a stage to make the isotopes of hydrogen that then go on to fuse to form helium. But you can see with this equation here for this part of the fusion reaction that it still follows the rules of the nuclear equations that we've looked at before. So these atomic numbers are balanced at the bottom and the mass numbers are balanced at the top. So it's the same skills that we're applying to lots of different situations. Now, one of the things that scientists would like to be able to do in the future is have a nuclear power station that was based on fusion instead of fission. There's a couple of reasons that we'd like this to happen. First of all, we like nuclear power stations because they do not emit carbon dioxide, CO2. and that's a good thing in terms of climate change and global warming. But fusion has the added advantage that it doesn't produce radioactive waste like nuclear fission does. So that means we don't have to store it and make sure that things aren't contaminated by the nuclear waste. Because the product of fusion is helium, which is useful, so that's fine. Now, we are conducting research into making fusion happen in man-made situations. This picture here is from the Joint European Torus JET, which is situated just south of Oxford. And this is a research centre that's been at the forefront of fusion research up until recently. They've just built a new research centre in Switzerland. And what they're looking at is how to make fusion take place so that we could eventually have it in a power station. Now, the problem currently that we have is that we need to put in more energy than we release, which means at the moment it's not commercially viable. But if we keep researching the process and improving it, the aim is that in the future we'll be able to use fusion within a nuclear power station. Now, one of the challenges that they have when trying to make fusion take place in a man-made situation is they're trying to replicate the environment that you have in a star. So that means we need a really, really hot gas. And in order to do that, so that the gas doesn't cool down, they use a magnetic field to keep a hot plasma gas from touching the walls of the reactor. Because if they touch the walls of the reactor, they'll cool down. So there's lots of challenges, but it's a very interesting area of research that hopefully will benefit us in the future. So that is the little fusion video there. Make sure you've got a summary of the key points and that you're clear about the idea of the differences between fission and fusion. One thing that you could do to check that you understand the differences between fission and fusion is do a Venn diagram. So any differences in the areas that they just have separately and any similarities in the shared areas in the middle. It's always a good way to check that you've understood the key processes.